Good afternoon. Welcome everyone to EPA's Cumulative Risk Assessment 2013 webinar series. This webinar series is co-sponsored by EPA's Risk Assessment Forum, Cumulative Risk Assessment Technical Panel, and EPA's National Center for Environmental Research. We are very happy that you are all able to join us today, and we continue to be very pleased with the high interest in this webinar series. My name is Devon Payne Sturges, and I am with EPA's National Center for Environmental Research. I am the Assistant Center Director for Human Health, and also with me on the line is my colleague Lawrence Martin, staff to EPA's Risk Assessment Forum. We are honored to have with us today two leading researchers and practitioners on cumulative risk assessment, Drs. Ramya Chari with the RAND Corporation and Thomas Burke with the Johns Hopkins Bloomberg School of Public Health. To accommodate our two speakers, we have extended the time for the webinar today to 4:30. So the first part of the webinar will last about 40 minutes to accommodate the two speakers, and once Ramya and Tom have presented, we will have approximately 30 minutes for questions and answers and discussion. Since there are many participants on the phone, and in order to ensure a successful webinar, all lines have been muted to minimize background noise. And also, I'm going to ask my colleague, Ashley Bubna, to go over the ground rules for the webinar.
While all lines have been centrally muted to reduce background noise, please also use the mute button on your phone if possible to avoid background noise, which can make it difficult for other participants to hear. If your phone does not have a mute button, it can be muted through the computer using the microphone button next to your name on the participants list on WebEx. Please note that muting using the WebEx participants list should only be necessary if you have accidentally clicked on your name in the WebEx participants box. All questions will be submitted using the chat feature in WebEx. These will be compiled, and the presenter will address as many as possible following their presentation. To access the participants list in the chat feature in WebEx, please click on the green tab at the top of your screen. This will expand the box, and you can click on the chat or participants, and a box will appear on the right-hand side of your screen. This webinar is currently being recorded and will be made available on the EPA INSER website.
Thank you, Ashley. Before we get started, Lawrence and I would like to say a few words about the purpose of these webinars. The purpose of this series is to share and discuss the progress of groundbreaking research on cumulative risk and other related activities to develop and apply methods for assessing the combined health and/or ecological risks of multiple chemical, physical, and/or biological stressors with consideration of population vulnerability. The series will feature scientists from both inside and outside EPA. Assessing or evaluating the true reality of environmental impacts on human health is a major challenge for EPA. From my perspective, there is no one approach to cumulative risk assessment. There is a spectrum, and our purpose with each webinar is to explore an aspect of that spectrum, of cumulative along that spectrum. Last month, we had a presentation on applying cumulative assessment in a regulatory decision-making context, air permitting in Minnesota. Today, we are going to hear about the use of epidemiological data for environmental decision-making in the context of cumulative risk, the importance of incorporating susceptibility in cumulative risk assessment using risk analysis for the lead NACs as a case example, and then we will wrap up the discussion with a few words from Tom Burke about the policy implications for cumulative in the context of the recommendations from the NAS that they provided to EPA in their report, Science and Decisions. Now, Lawrence, could you say a few words about the Risk Assessment Forum's efforts on cumulative risk and how today's webinar helps to address these important issues for the RAF?
Panel and EPA's Office of Science Advisor. EPA has been engaged for a number of years in the development of the guidelines for cumulative risk assessment, or CRA as we call it. It's not a simple matter. The work is performed by a cross-agency technical panel of the Risk Assessment Forum, or RAF, in the Office of the Science Advisor. The RAF CRA Technical Panel published the framework for CRA in 2003. See the link on the slide. This was our first step in mapping out strategies and methods to conduct a CRA, and it's something that we're still very much engaged in. The RAF is very happy to partner with ENSO to present these webinars of current and cutting-edge thinking on CRA, and it's as much a service to our technical panel as it is to the wider scientific community. The panel members listen to both the speakers and the dialogue following the presentations to gain insights to CRA methods and applications. And I want folks to be sure to note that we're interested in your ideas and any concerns that you have about CRA, and we want to hear from you. So here's the CRA technical panel roster. As the technical panel explores methods for combining and integrating chemical and non-chemical stressors, we've increasingly looked at the validity of epidemiological methods. And I'm very interested to hear more about how Drs. Burke and Chari are using epidemiological data for environmental decision-making in the context of cumulative risks. Similarly, the inclusion of susceptibility information into CRA is considered an essential dimension of what we're doing, and we're very interested to understand the approach that they advocate. As Devon noted, Science and Decisions is, an influential publication by the NRC, and it was chaired by Dr. Burke, the panel that wrote the publication. And this has provided the RAF CRA technical panel with key guideposts for our guidelines development for a couple years now. And I'm very happy on behalf of the technical panel to welcome him and his colleague, Dr. Chari, to the EPA CRA webinar series. Thanks.
Well, thank you, Lawrence. Now I would like to introduce Drs. Ramya, Chari, and Thomas Burke, our 5th and 6th speakers for our series. Ramya and Tom's presentation is entitled Integrating Susceptibility into Environmental Policy, Implications and Information Needs for Cumulative Risk Assessment. Ramya is an associate policy researcher at the RAND Corporation. She has expertise in environmental health risk assessment, environmental epidemiology, and the assessment of population exposure to environmental pollutants. Dr. Chari's research includes the development of metrics for evaluating cumulative chemical exposures, community-level health assessment of environmental risks, and assessing and measuring emerging environmental threats to national health security. Thomas A. Burke is Associate Dean for Public Health Practice and Training and Professor in the Johns Hopkins Bloomberg School of Public Health, Department of Health Policy and Management, with joint appointment to the Department of Environmental Health Sciences and the School of Medicine Department of Oncology. He is also director of the Johns Hopkins Risk Sciences and Public Policy Institute. Dr. Burke is chair of the National Academy of Sciences Committee on Improving Risk Analysis. His research interests include environmental epidemiology and surveillance, evaluation of population exposures to environmental pollutants, assessment and communication of environmental risks, and application of epidemiology and health risk assessment to public policy. So Ramya will speak first, then Tom, so I'm going to turn this over to Ramya.
Thank you, Devon, for your introduction. Tom and I are both honored to be invited to present to the Risk Assessment Forum. And as Devon noted, today we will be talking about the incorporation of susceptibility into cumulative risk assessment. And I will first be discussing a case study that we carried out in order to illustrate the importance of assessing susceptibility in policy decisions, as well as to understand some of the current limitations that need to be overcome before we can realistically and systematically consider susceptibility in a more practical fashion. And then following that, Tom will discuss a new framework for cumulative risk assessment that came out of his work as chair of the National Research Council Committee, as well as recommendations for EPA to consider for integrating CRA into decision-making, or most people, and why they might be more greatly affected. And when we actually do have knowledge of who might be more susceptible to chemical toxicity, we tend not to know how much more susceptible they might be. And so when our data is sparse, we use conservative assumptions in risk assessment, and this is believed to result in policies that should be protective of the most vulnerable groups. However, really our limited knowledge about the extent and impact of susceptibility in the population tends to undermine these assumptions. Because how can we know that we are being protective if we don't actually have data that can give us an idea of the bounds of susceptibility? And so there's no way to test if our assumptions are actually true. And so these data limitations for considering susceptibility are
are a real barrier, and the EPA framework for cum risk assessment does recognize this by saying that the extent to which susceptibility can be considered in CRA will be heavily dependent on existing knowledge and available information. Now, when we talk about susceptibility, we use the definition described by Ken Sexton as characteristics of an individual or population that alter biological response to environmental insults. And we will also talk about susceptibility factors, as originally described by Grassman, and I'm happy to provide references to anyone who would like them. And so susceptibility factors are essentially risk factors related to susceptibility that influence the response to an exposure in terms of severity of response or the type of response you might have. And in essence, susceptibility factors act to increase susceptibility. And there are two general types of these factors, intrinsic and acquired characteristics, and both can act to alter one's biological response to a chemical toxicant. Now, intrinsic characteristics are fixed or inherent aspects of an individual. For example, these could be age, race, ethnicity, gender, or genetic makeup. And acquired characteristics are variable or modifiable traits obtained through things like one's lifestyle choices or behaviors or environmental surroundings. And so these could be things like smoking, diet, disease state, stress levels, or socioeconomic status. Now, one consequence of neglecting differential susceptibility in policy development might be the continuation of environmental health disparities. And this is the idea that has been proposed that persistent socioeconomic health disparities are not solely the result of greater environmental exposures in low-income populations, but might also arise from low SES populations displaying greater susceptibility to the same exposures. In this case, acquired characteristics become particularly important because of their direct policy relevance. And by this we mean that these are modifiable factors that are amenable to intervention, and they might help explain these persistent socioeconomic health disparities. And in fact, a number of potential acquired susceptibility factors have been studied in the literature as effect modifiers of chemical toxicity, and the bulk of these studies have actually focused on lead. But these studies include factors such as high stress levels, nutritional deficiencies, disease or comorbid conditions such as diabetes, and even SES itself. And many of these factors could be considered to be potential mechanisms or pathways through which socioeconomic health disparities may operate, as they tend to be more greatly concentrated in economically disadvantaged populations. And so in order to delve into the incorporation of susceptibility into environmental policies, we carried out a case study looking at the process through which EPA set the 2008 National Ambient Air Quality Standard for lead, or the lead NAAQS. And we carried out this case study in order to determine how consideration of susceptibility may affect policy decisions, and also to determine how characterization of risk may change when susceptibility is explicitly and quantitatively considered in policy development. And so what we did was present alternative scenarios for developing a lead NAAQS by considering populations who may be more highly susceptible to lead toxicity. So first, I just want to briefly give you some background of how EPA set the 2008 lead NAAQS. Now, in 2008, the NAAQS was revised and set at a level of 0.15 micrograms per meters cubed with a rolling 3-month averaging time and a maximum not to be exceeded form evaluated over a 3-year period. And so this was actually a substantial revision downward from the original 1978 standard of 1.5 micrograms per meters cubed. And the original standard was actually developed to protect children against anemia and impacts on the heme synthesis pathway, and it also considered neurological and renal effects. And it was based on preventing most children in the U.S. from having a blood lead level that exceeded 30 micrograms per deciliter. And now the Clean Air Act requires that EPA revisit the National Ambient Air Quality Standards every 5 years. And up until the 2008 revision, EPA didn't make any changes to the lead standard. And for the 2008 revision, however, the agency reviewed over 6,000 scientific studies and assessed a range of risk assessment, experimental, and epidemiological data. And in the end, the NAAQS was developed using what EPA called an air-related IQ loss framework. And this actually marked a departure from the development of the original lead NAAQS by moving from an exposure-based approach to an effects-based one. And so what I mean by that is that EPA moved away from determining an appropriate target population mean blood lead level and instead focused on determining the effects of air lead on the critical health effect of concern. And this was neurocognitive deficits, or IQ loss in children. EPA also decided to focus more on published studies, and in particular epidemiological data, in order to quantify the relationship between air lead and IQ loss in children. And so in terms of decision-making, this framework meant that EPA would make decisions based on the amount of IQ loss in children that would be expected at different candidate levels of the air standard. Now, IQ loss was estimated through the following equation written here, where beta times A times B equals IQ loss. And in this case, beta is an estimate taken from epidemiological studies that relates changes in blood lead level to changes in children's IQ. And this estimate is also known as a concentration response function, or a CR function. And so also in this equation, A refers to the potential standard level that EPA considered, and B equals the air to blood lead ratio. And so this is a ratio that, as the name implies, is needed to translate air lead concentrations into blood lead concentrations so that EPA could go from an air standard level to a blood lead level and then determine IQ loss from there. So based on that equation that I just presented, we can see that there are three main parameters to consider: a CR function, an air to blood lead ratio, and a standard level. Now, the CR functions were determined through a pretty comprehensive and thorough review of the epidemiological literature. And in the end, EPA chose 4 studies from which it pulled CR functions. And all 4 of these studies focused on children and looked at the effect of blood lead on measures of intelligence. And I won't go into the details of the individual studies now, but again, I'm happy to provide references. But the CR functions from these studies displayed a range of IQ loss as a result of lead exposure, and EPA chose the median value for their analysis. And this value was an expected loss of 1.7 IQ points per microgram per deciliter blood lead level. And EPA also assessed a range of air to blood lead ratios, and they considered 3 values, 1 to 5, 1 to 7, and 1 to 10, where 1 represents air lead, and the second number represents blood lead. And then for the third parameter, EPA assessed a range of potential lead standards from 0.02 all the way up to 0.5 micrograms per meters cubed. And finally, there was actually a 4th consideration. Given that lead displays no threshold in the literature, meaning there is no evidence of a safe level at which one can be exposed to lead, EPA had to decide on an acceptable level of risk. And in this case, acceptable risk was operationalized as an acceptable loss of IQ. And so based on discussions and guidance from the Clean Air Scientific Advisory Committee, EPA decided that an air-related IQ loss of 2 points should be used. And so this means that whatever standard is chosen should guard against a population mean IQ loss of no greater than 2 points in the more highly exposed populations, or the subset of children likely to be exposed at the level of the standard. So in our case study, we wanted to determine how explicitly considering susceptibility may affect the decisions made by EPA using the same decision framework that the agency used to set the lead NAAQS. And one critical piece of EPA's analysis was the choice of CR function. And the CR functions evaluated by EPA represent the main effects of blood lead on children's IQ while controlling for other risk factors, meaning that the effect of blood lead is not expected to vary across levels of another factor. And just as an example, one might say that there is no expectation that the effects of blood lead on IQ would change depending on whether you were male or female, or that males would exhibit a much worse response than females to the same lead exposure. Now, in order to test this idea that lead toxicity does not vary across risk factors, we carried out a systematic review of the literature to identify the types of acquired susceptibility factors that had been studied in regards to lead toxicity. And we found that socioeconomic status was actually the most studied factor, acquired factor, and the literature does provide some suggestion that the effects of lead may vary across socioeconomic position. So certain studies have found that children in lower SES groups tend to exhibit greater loss of neurocognitive function as a result of being exposed to lead compared to higher SES groups. And we chose to focus on SES as our susceptibility factor of interest for our case study due to the number of studies that focused on it, as well as relevance for public health policy. So to carry out our analysis, we essentially followed EPA's approach using the same equation where IQ loss equaled CR function multiplied by standard level multiplied by air to blood lead ratio. And we conserved EPA's selections for candidate standard levels and also the air to blood lead ratios. For the CR functions, however, we identified and assessed a range of functions developed through studies that examined SES as an effect modifier of lead neurotoxicity, meaning that the studies examined whether the effect of lead varied depending on what socioeconomic strata you were in. So to identify these CR functions, we did a systematic review of the epidemiological literature looking for any study that assessed socioeconomic subgroup effects for lead neurotoxicity. And we ended up identifying about 40 studies that explored SES as an effect modifier or looked at lead effects across different SES groups. However, only a small subset of these studies, around 4 of them, provided enough information to actually pull out CR functions for low and high SES groups. And again, I won't go into detail about these 4 studies now, but can provide the rest. So now I would like to take you through this figure, which illustrates both EPA's results as well as our own. So this figure illustrates the range of IQ loss estimates expected at each potential air lead standard. And so we can see air lead standards on the x-axis and response, or the estimated IQ loss on the y-axis. And the estimated IQ losses per standard level that were calculated by EPA are shown as triangles. And so note that these estimates of IQ loss were generated using the equation of CR function, which in this case was that median value of negative 1.75 IQ points per microgram per deciliter blood lead, multiplied by the candidate standard level, which are shown on the x-axis, and then multiplied by the air to blood lead ratio, which in this case was the central ratio of 1 to 7. Now, this dotted line represents EPA's acceptable risk level of no more than a 2-point loss in the population mean IQ for the subset of children exposed at the level of the standard. And so we can see that the standard of 0.15 micrograms per meters cubed fulfills this decision criterion. And this is generally how EPA decided on the standard level. Now, we can see some differences when we apply the results of our case study. So here we present expected IQ loss when using CR functions developed for low SES and high SES groups, so considering differential susceptibility by socioeconomic status. And the squares represent estimates for low SES groups, and the circles represent estimates for high SES groups. And so we can see, compared to EPA's values, we note that there is a greater estimated IQ loss for low SES groups at all potential standard levels. And then under the 0.15 micrograms per meters cubed standard, the loss in IQ for low SES groups actually exceeds the 2-point acceptable risk level set by EPA. And now at standard levels above 0.15, only estimates derived from high SES groups, which are the circle symbols, fall under or close to the acceptable risk level. And at standards below a level of 0.1, IQ loss estimates from all groups meet acceptability requirements. And so based on using these socioeconomic subgroup-specific CR functions, we can see that in our case study, the decision calculus might be shifted to include consideration of a standard level of 0.1 micrograms per meters cubed. And by using CR functions that don't account for the possibility of increased susceptibility in, as in this example, lower SES groups, EPA's IQ loss framework may not protect the target population to the desired extent. Now, we do want to caveat our findings. First of all, we note that the epidemiological literature currently provides only suggestive evidence of SES as an effect modifier of lead neurotoxicity. And there are healthy debates over the results of the 4 studies that we were able to include in our analysis. For example, one of our chosen studies was a prospective analysis carried out in a Cincinnati cohort, and the authors found significant interactions between SES and lead in earlier but not later years, indicating that maybe differential effects may not persist or may be attenuated in later years by some undetermined circumstances. And there are other issues also related to comparability of exposure measures and outcome measures and socioeconomic status measures across the 4 studies, which lead to uncertainty in our analysis. And so we chose these 4 studies not because we believe them to be the best 4 out of the universe of studies we identified, but because they were the ones that we could actually pull out estimates for. And so these studies do not by themselves provide definitive evidence about the existence or the magnitude of socioeconomic interactions with lead. Another important thing to note that I didn't put on the slides is that we concentrated mainly on the standard level of 0.15 micrograms per meters cubed. But the air lead standard is made up of other parts, including an averaging time and form, and these pieces were also directly relevant to EPA's selection of a final standard, though we didn't focus on these properties in our analysis. So it is actually the standard level of 0.15 micrograms per meters cubed in conjunction with a rolling 3-month averaging time and a maximum not to be exceeded form that, according to EPA, would significantly reduce and limit for a high percentage of U.S. children the risk of experiencing an air-related IQ loss of 2 points. And so a number of decision elements also went into selecting the averaging time and the form. And so we recognize that the effect of socioeconomic position on lead neurotoxicity is a complex phenomenon. And our case study was a simplified assessment done not to say that EPA got it wrong in this case or that their analysis should have been done using the studies that we chose or that the standard needs to be lowered now, but rather to illustrate the need for understanding susceptibility in ways that are policy relevant and to make concrete what the data needs and limitations are in order to do so. And so finally, I would like to talk about some of the implications of our work. Our case study showed that there really is a great need for quantitative information on susceptibility if we are realistically included in our policy decision frameworks. And this can't be just a qualitative exercise or a thought process, because in the end, there really is not as much debate over whether certain population groups might be more susceptible. The question in the debate really is over how much more susceptible these populations really are. And that's what we need to know if we are to craft policies that are actually protective of all population groups. And now in the absence of data, there is research that indicates that individuals are pretty bad at making complex and unaided decisions. If we have no information, then we have no frame of reference for where to put the bounds around susceptibility. And so without explicit and quantitative consideration of susceptibility, policy decisions may be less protective and even less equitable. And so if we can quantify susceptibility, this will allow for more informed choices, for better assessment of decision consequences, and as well as increased accountability and transparency in policy development. In addition, quantification can help to clarify decisions regarding acceptable risks and make decisions transparent regarding whether population differences in risk are acceptable. And so in this case, EPA selected a risk level of 2 IQ points, and in their justification, they noted that there is a lack of accepted criteria within the public health community for the appropriate degree of protection afforded to neurocognitive effects in susceptible populations. And so unlike with carcinogens, where 1 in a million has tended to guide acceptable risk decisions, for non-carcinogens, issues of acceptable risk are being made without any historical guidance or really any guidance whatsoever. And because of this, decision makers must make what could often be controversial choices regarding what level of risk or loss of function is acceptable and to whom. So now the NRC committee that Tom chaired has recommended that EPA unify cancer and non-cancer dose response assessments. And this may result in a greater number of non-cancer chemicals evaluated evaluated under a no threshold model. And there are signs that EPA is indeed moving in this direction. And so in the future, we might be seeing less of these, regulatory, quote-unquote, bright lines indicating safe exposure levels and more deliberation over acceptable risks. And based on this, it really becomes more important than ever to include susceptibility in policy decision-making, as risk decisions can already be really difficult and controversial and are definitely subject to criticism from different stakeholders. And the determination and the acceptability of quote-unquote, acceptable risk really depends on the population to which it is applied. And so these decisions need to be made transparently and openly, and quantification of susceptibility can help with that. And finally, quantification can help prioritize and focus risk management decisions by providing an understanding of who might not be covered under current standards or current policies, and who might need more targeted interventions. And there are different routes to go when considering susceptibility in decision-making, and understanding susceptibility actually opens up a range of possible risk management actions. So do we need to set a very conservative standard that is sure to protect everyone, or could we set a higher standard and then focus on more targeted interventions aimed at susceptible groups? Also by focusing on susceptibility, we can open up a greater range of interventions to consider. So it's like two sides of the same coin, right? On the one hand, we can focus on lowering exposures, but on the other hand, we can also focus on reducing susceptibility. And so for lead, this might mean ensuring adequate calcium or iron intake in high-risk populations, or implementing, say, stress mitigation programs if these factors are actually shown to modify lead toxicity. And so with that, I would like to turn it over to Tom.